In this series of lectures, we'll talk about the directional properties of crystals, in particular conductivity, stress strain, and elastic moduli. The outline of these presentations will include first a review of coordinate transformations and review of the rotation or transformation matrix, review of what a direction cosine is and what Euler angles are. Finally, we'll move into tensors, and I'll give an introduction and rules for transformation for tensors, talk about crystal symmetry constraints, and I'll look at some individual cases of elasticity in different minerals and connections to elasticity, including isothermal compression, acoustic wave velocities, isothermal to adiabatic conversion, which is something that I won't get to, and then aggregate averages, including lattice preferred orientation and the isotropic limit of aggregates. Now this should be all old hat. I expect you to know the basics of vector and matrix operations. And just for review, consider the coordinate system as shown, and consider a new coordinate system with primed coordinates that has been rotated some angle theta. We can look at the new x-coordinate as a vector with projections onto the old xy coordinates as shown with a projection onto the x-axis, which is the cosine of the angle theta, and a projection on the y-axis, which goes as sine of the angle theta. And then there's no projection onto the z-axis, so we have 0, and we have then a triplet vector for the x-prime axis. Now, of course, the same angle theta applies to the y-prime axis as shown there, and y-prime can be represented as vector components of the xy coordinate system as shown. And of course, in this case, z prime is the same as the old z. Putting this all together, we can write it as a matrix operation where the primed coordinates are equal to a matrix times the unprimed coordinates. This matrix transforms coordinates x, y, z into the primed coordinates x prime, y prime, z prime. And I'll just remind you that the convention is that the angle theta is measured in a counterclockwise direction. Now these rotation matrices rotate about various axes. Here's an example of a rotation matrix about the x-axis. And a rotation about the y-axis would be this matrix. And the general idea is that a vector can be rotated when it's multiplied by a transformation matrix. If the vector is a coordinate axis, the rotation transforms the coordinate system to a new, call it the primed set of axes. So we have a matrix A multiplying a vector V, giving us a primed vector V prime. Now the V prime vector can be rotated yet again about its new coordinates, and here is a new transformation matrix A2 multiplying the primed V, giving us a double primed V. So you'll notice that double primed V is related to the original V by two matrix multiplications. First rotating about the x-axis and then rotating about another axis. We can write that compound vector, our compound rotation process, as the product of two rotational matrices, A2 times A1. Now an important note is that matrix multiplication is not a cumulative process. The A2 times A1 is not equal to A1 times A2. And in many cases, we'll substitute numbers for the x, y, z, giving us 1, 2, and 3 axes. We can write a general transformation matrix A as this matrix here. And we can think of it, the insight is, place the old coordinates x, y, z across the top, and place the new coordinates x prime, y prime, z prime along the side. Converting to new coordinates, you go across the matrix. So, for instance, the x prime axis is equal to axx times the old x, axy times the old y, and axz times the old z. These aij are the cosines of the angles between the ith and jth axis, and we'll call those the direction cosines. Now, similarly, we can write the expressions for the y prime in terms of the old xyz prime or xyz axes. Now we can go back from the primed axes to the old coordinates simply by looking at this transformation matrix in a vertical direction. So the z-axis is equal to the highlighted components of the x prime, y prime, and z prime new axes. So there it is. Z is equal to axz times x prime, yz times y prime, and azz times z prime. And similarly for the other axes. Important in this transformation matrix is, as a collection of direction cosines, the sum of squares of any row or column has to be 1. And in general, the primed coordinates are gotten by multiplying a times the original vector. And the original vector can be obtained by multiplying the transpose of this A matrix times the primed coordinates. Euler has a theorem that says that any generalized transformation can be accomplished by 3 sequential rotations. You need a convention about which axes you're going to do the rotations and in what order. Given 3 rotations, you can describe them in terms of 3 Euler angles, and I'll call them alpha, beta, and gamma. And notice that the transformation matrix A has 9 elements, but the Euler angles are 3 numbers. The extra degrees of freedom are in defining what the axes are. So there's a Euler convention called the CoQ Convention, in which the first rotation by angle alpha is done about the z-axis. After rotating about the z-axis, rotate about the y prime axis by the angle beta, and then finally rotate about the z double prime axis by the angle gamma. This is a compound set of rotations starting on the right side with the first rotation, in the middle the second rotation, and on the far left the last rotation. The matrix product here then gives you a compound Aij that describes the full rotation. I have to let you know that there's also a Bunga Convention, in which instead of in the second rotation rotating about the y-axis, it's rotation about the x prime axis. This gives a set of individual rotations that looks like this, very similar to the preceding, except the middle matrix has the one in the x position rather than in the middle of the matrix. Now, in different instruments and different papers, you'll find either the CoQ or the Bunga convention used for Euler angles. For instance, HKL uses the Bunga convention, and so when using Euler angles, you always have to confirm which convention is being used. Now here's some additional notes. You can write down the transformation matrix in trivial cases when it's a rotation about a coordinate axis. We've already done that. We can also construct a transformation matrix by giving 3 angles. I've provided you a MATLAB function called Euler.m, and to use that, here's an example. A matrix is equal to Euler, and within the parentheses of this function there's a square bracket which encompasses numbers that are to be combined together into a vector. So we have a vector 0, 0, 0, so 0 rotation on each axis. And of course, MATLAB will spit back to you the identity matrix where the mapping is x goes to x prime, y goes to y prime, and z goes to z prime. Now if I give it some definite angles of rotation, then the A matrix is not so simple. I also provide you with an inverse Euler function which returns the Euler angles given a transformation matrix. So if you type in inverse Euler of A, it will spit back to you the angles that you put in. So now, MATLAB knows rules for matrix multiplication. So I'll show this by letting you work through this example. Let's define a transformation matrix A1 as Euler and only one rotation, the first alpha angle. That returns A1 looking like this. If I type in A2 with a rotation in the beta location, that will give me this matrix. And if I type in the third angle and 0 for the other two angles, I'll get this matrix. These are the three angles that I used in the previous slide. Now I can do the composite rotation, which is A1 rotated by A2 rotated by A3, simply by matrix multiply A3 times A2 times A1. And this returns a transformation matrix of this form, which is exactly the same as the transformation matrix you would have gotten if you typed Euler with those three angles in the argument. Now we can also determine transformation matrices by inspection. For instance, a mirror plane in the zy plane would map x into minus x, y goes to y, and z goes to z. And that gives us a very simple transformation matrix like this. I could also define a 45-degree diagonal mirror plane where x goes to y, y goes to x, and z goes to z, which would look like this. Or I could rotate 90 degrees about the z-axis where x goes to y and y goes to minus x and z goes to z, which would be a matrix that looks like this.